So we'll be going to study on programmable read-only memory. Programmable read-only memory is also known as abbreviated as PROM, programmable read-only memory. AND array with buffer inverter is an n to 2 raised to n line decoder. OR array is a collection of programmable OR gates. Okay, so here we have AND array also and OR array also. In PROM, AND array is fixed. Okay, it is nothing but n to 2 raised to n line decoder AND array. OR array is programmable, that is fuses can be blown or you can have the desired functional values here. Decoder is a minterm generator. N variable minterms appear on the 2 raised to n lines at the decoder output. These are also known as word lines. Okay. Next, n input lines are called address lines. M output lines are called bit lines. Here you can see that 2 raised to n lines at the decoder output are known as word lines. Input lines are called as address lines. Output lines are called as bit lines. How do we characterize the PROM? We characterize it by 2 raised to n cross m. M is the bit lines. Output lines are called bit lines. 2 raised to n is the decoder output. 2 raised to n at the decoder output, and these are known as word lines. So we can realize the Boolean expression using this PROM as how we had done it in using decoders. Yes? So this is a PROM structure. We have x0, x1, xn minus 1 inputs connected to these inverters or buffers. The output of this, okay, so we have here, actually we have here what we have, x0 we have. What we have here, x0 bar we have. Similarly, here we have x1 output. Here we have x1 bar output. Here we have xn minus 1. Here we have xn minus 1 bar. So, together we get true outputs as well as complemented outputs. If suppose you are getting x0 as the output as true value, you will be getting x0 bar as the complemented value. These true and complemented values are connected to the AND gates, and then the output of these AND gates are connected to the OR gates. As you can see here, AND gates are fixed. OR gate is programmable. Hence the fuses are connected here. You can see these fuses now, students. So here OR gates are programmable. So the fuses are connected. So AND gates is fixed. Okay. OR gates is programmable. Okay, so in PROM structure, students, in PROM structure, AND array and OR array both are present. In all the PLD devices, AND array and OR array are present. AND array is fixed, OR array is programmable. Okay, so OR array is programmable, you can see here. Programmable means the fuses are connected. AND array is fixed, so dots are connected here, isn't it? Fine. So now here in PROM we studied that AND array is fixed, OR array is programmable. So here you can see this x0 bar is there here, x0 bar, x1 bar. Similarly, xn minus 1 bar. Both true and complement outputs are connected to this AND gate array. Now here you can see. See, this is first three input means what you will have. See here, x0, x1, x2. Three input means 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So first what we have 0, 0, 0. So here 0, 0 complemented no here. So 0, 0, 0. Next what we have, this is complemented 0. This is complemented 0. This is 1, 0, 0, 1. Up till similarly we have last one as 1, 1, 1. So true values. These are true values. 1, 1, 1. So from 0, 0, 0, 0, 0, 1 up till 1, 1, 1 we have combinations here produced. So these product terms are generated at the AND gate array. Product terms are generated. Whichever product term is there in the F1, that will be selected. Whichever product term is present in the F2, that will be selected for function F2. Similarly up till M. Okay. How do we categorize this PROM? 2 cross N cross M. 2 cross N, here we have 2 cross N. Here we have M functions. So 2 raised to N cross M. 2 raised to N is a decoder output. M is the F output lines. Okay, this is how we study about the PROM structure. AND array is fixed. AND array is fixed 0, 0, 0, 0, 0, 1 up till 1, 1, 1 combinations we get. The product terms are generated at the output of the and the functions are realized at the OR array. Okay, so here we have fixed AND array decoder and we have programmable OR array. Programmable OR array means we have fuses. Here what we have programmable means we have fuses. Okay. So next we will solve an example in this, students. So given an example, f1 x2 x1 x0 is equal to summation m 0 1 2 5 7 f2 of x2 x1 x0 summation m 1 2 4 6. How to do this? So it is a 3 variable x2 x1 x0. Write 0 0 0 0 0 1 up till 1 1 1. Write f1 and f2 at the output column. F1 is having 0, so it is 1 here. F1 is having 1, so it is 1. F1 is having 2, so it is 2. Next 5, so it is 1 here. 7, so it is 1 here. So wherever F1 is 1, 0, 1, 2, 5, 7. Write it 0, 1, 2, 5, 7. Next F2 where it is 1, 1, 2, 4, 6. So 1, 2, 4, 6. So write here 1. Okay. Wherever functional value is there 1, 2, 4, 6. First write the truth table. Then draw how many inputs are there? 3 inputs are there. X0, X1, X2. For that particular 1, 1 inverter or buffer you draw. And then draw the true value, complemented value. Similarly for x1 true value, complemented value. True value, complemented value. Okay. So first you have 0, 0, 0. It is done. Junction dot. Next we have 0, 0, 1. Next we have 0, 1, 0. Next we have 0, 1, 1. Next 1, 0, 0. Next we have x2 is 1, 0, 1. Next 1, 1, 0. Next 1, 1, 1. So here we have all the product terms generated from these 8 AND gates. So here we have product term. What will be having here? X0 bar, X1 bar, X2 bar. Here also we have similarly, we have at the end X2, X0, X1, X2. 1, 1, 1 and this is 0, 0, 0. So we have a product terms generated here from 0, 0, 0, 0, 0, 1, 0, 1, 0 up till 1, 1, 1. We have a product terms generated at the output of this AND gates. So in F1 0 is there? Yes. So put a cross mark. 1 is there in F1? Yes. So put a cross mark. 2 is there? Yes. So put a cross mark. 5 is there? Yes. So put a cross mark. 7 is there? Yes. So put a cross mark. Okay. So that function will be realized by this F1 function. Summation M of 0, 1, 2, 5, 7. Next. 1 is there in F2, 2 is there in F2, next 4 is there in F2, next 6 is there in F2, so that will be realized by function F2. So this is the solution, using PROM. So in PROM what we will do is, as you know that AND array is fixed, OR array is programmable. AND array means it is nothing but a decoder. Okay, it will generate a specific canonical terms it will generate. Whichever the function F1 is having 0, 1, 2, 5, 7, there you put a cross mark indicating a connection is done. Next F2 is having 1, 2, 4, 6, there you put particular 1, 2, 4, 6 here. 1, 2, 4, 6. Put a cross mark indicating that connection is there. It will realize a function F2. Okay. So going to the next. Why it is called PROM? 3-bit input combination to X0, X1, X2 lines is regarded as address of the one of the words. Okay. So the input lines are there, no? X0, X1, X2 lines. Those are known as address of one of the word lines. As a consequence of selecting a given word line, a pattern of zeros and ones, a word is determined by the fusible connections to the selected word line appears at the bit line of the device. Now here we have the 0, 1 pattern is considered the word stored at the address associated with the selected word line. Okay, so here we have 3 types, that is input lines. We have no input lines X0, X1, X2, all these things are known as address lines. Input lines are address lines. Output of the decoders are there, no? Output of the decoders, those are known as word lines. And the output lines are there, no? Output lines, those are known as bit lines. So 3 are there. Address lines, we have address line. At the input buffers are there, no? Input lines, those are address lines. Decoder output of the AND gates are known as word lines. Output lines are nothing but known as bit lines. For example, now here the word stored at the address X2, X1, X0 is equal to 1, 0, 0 is F1, F2, 0, 1. That is when X0, X1, X2 are 1, 0, 0, X2, 1, 0, 0, F1, F2 values are stored as 0 and 1. So this min term is not present in F1 function. This min term is present in F2 function 4, that is 100. The meaning of this statement is this only. 100 is present at F1. 100 is not present at the F1. It is present at the F2. Okay. So with this, I think you know X0, X1, X2 lines are nothing but address lines. The output of the decoders are nothing but word lines. The output lines are nothing but the bit lines. The entire slide says that the word stored at the address is 100. Okay, it is nothing but F1, F2 output bit lines are 0 and 1. So read only. The fact that the connections associated with the fusible links normally cannot be altered once they are formed. Read only memory means you cannot alter it, you cannot change it. Okay, you cannot edit it. Read only means you can only read it, you cannot edit it. Okay. So next type of PLD, that is programmable logic array. PLAs are characterized by three numbers: number of input lines n, number of product terms that can be generated p, that is the number of AND gates, and number of output lines m. So how do we characterize the programmable logic array? N cross P cross M. N we have already told. What is N? What is N? N is the input lines. What is P? P is the product terms which is generated at the AND gates. Okay. What is M? M is the output lines, the number of output lines. So now typical PLA is 16. 16 input lines are there. 48 product terms are there at the output of the AND gate. Next 8 output lines are there. In programmable logic array we have AND array also, we have OR array also. Both are programmable. Both are programmable. Okay, both are programmable. So here we can see programmable logic array. Here programmable AND array. See, you can see the fuses here. You can see the fuses here. You can see also the fuses here. Okay, so AND array is programmable. You can see that AND array is programmable because fuses are connected. Here also OR array is also programmable. OR array is also programmable, right? We can have a desired connection using these fuses. Okay, so it is not necessary to generate the canonical terms only. It is not necessary to generate the canonical terms only. Product terms are generated which may not be canonical in nature. Okay, because AND array is programmable. Whereas in PROM, what we studied in earlier PROM AND array was fixed. AND array is fixed means the canonical terms were generated in PROM. Whereas in PLA, because AND array is programmable, whichever connections the user wants, the user desires, those connections only can be kept. Other fuses can be blown out. Okay, so we can also have canonical terms, we can also have non-canonical terms. That means, what does this mean PLA? Because both the array are programmable, we can somehow minimize the expressions. Whereas in PROM we had canonical terms, whatever the product terms were generated, those only we used to have a connection. We make a connection using a cross mark and realize the function F1 and F2. Whereas programmable logic array, both are programmable, so we have more flexibility. How do we characterize this? N cross P cross M. N is this input lines, P is this number of product terms, M is this output lines. This is how we characterize the PLA. We have a typical 16 cross, 48 cross. We had a typical PLA size. It is 8. Okay. So we have 8 here. 8 is what? 8 is the number of output lines. 6 is the input, 48 is the product term, 8 is the output line. One thing you remember that programmable logic array, both AND array and OR array are programmable, hence it is more flexible and generates non-canonical terms. Generate non-canonical terms also. Desired connections can be done by the user by using this fusible links. So continuing programmable logic array, in many logic design situations, not all the minterms are necessary for a realization. All the minterms are not needed for a realization. For n input variables, 2 raised to n minterms are generated. This is the number of gates in the AND array of a PROM, isn't it? So in PROM, what we used to do? PROM is characterized by 2 raised to n cross m. PLA is characterized by n cross p cross m. 2 raised to n is decoder output. M is the output line, right? PLAs with 16 input lines, 2 raised to 16. How many minterms we will get? 65,536 minterms. So many minterms are not necessary for the realization, isn't it? It is not practical also. So in a 16 cross 48 cross 8 PLA, only 48 product terms are there. 16 is the number of input lines, 48 is the number of product terms, 8 is the number of output lines. 2n input appears at each AND gate. N or 2n inputs appear at the each AND gate, which will be seen in the next coming. For our example, assume 3 cross 4 cross 2. Students, here I would like to tell, in market 3 cross 4 cross 2 PLAs are available. PLAs are in standard in size. Standard size are there. 3 is what? Number of input lines. 4 is what? Number of product terms. 2 is what? Output lines. So standard sizes of PLAs are available. Those standard sizes only we can use. Okay. PROM versus PLA. Okay. So PROM versus PLA. I would like to tell that PROM is characterized by 2 raised to n cross m. PLA is characterized by n cross p cross m. 2 raised to n is the decoder output. Okay. M is the output line. N is number of input line. P is number of product line. M is the output line. In PROM what we do is we realize a set of Boolean functions which is basically minterm canonical expression. In PROM we have AND array fixed. So it generates canonical term 0 0 0 comma 0 0 1 up till 1 1 1 it generates minterm canonical expressions. No minimization is necessary and we cannot minimize the expression in PROM. Whatever it is given, just we put a cross mark and connect it and realize it in PROM. In PLA what happens? The AND gates are capable of generating product terms that are not necessarily minterms. Minterms means what? All the variables should be present. Minterm. So the PLA can also generate like this. See here, x bar y. It can also generate like this. Y z. It can also generate y z bar. But PROM generates only canonical minterms. Canonical terms. Okay, only min terms. PROM can generate only min terms, whereas PLA can generate whichever product terms we require, not necessarily the min terms only. Realization using PLA is based on sum of product expression that may not be canonical. Okay. So what happened here? Students, is the slide visible? Students, is the slide visible now? Yes. So here logic designer is bounded by the number of product terms that are realizable by the AND array. Simplifications is necessary in PLA, whereas it is not necessary in PROM, and the array is fixed. So here one example is given. Given f1 is equal to summation m 0, 1, 3, 4, f2 is equal to summation m 1, 2, 3, 4, 5. Implement it using 3 cross 4 cross 2 PLA. How do we do this now? 0, 1, 3, 4 for f1. Okay, 0, 1, 3, 4. So we put ones wherever f1 is there, we just put ones and then group
Excuse
it.
me, ma'am.
Yes.
Presentation. Ma'am, presentation is not visible.
So here given f1, f2 are given. So we have to implement it using PLA. Size also is given 3 cross 4 cross 2. Okay. So 3 is the number of input lines. That is a 3 variable x0, x1, x2. 4 is the number of product terms. 2 is the functions. How many functions we have? F1, F2. So 2 is the number of output lines. That is number of functions given. Okay. F1 and F2. Now here, see here, F1 is given 0, 1, 3, 4. 0, 1, 3, 4. Group it, write the prime implicants. So whenever you group it now, you will get this x bar, y bar here, x bar, z here, and next y bar, z. Okay. So whenever you group this, you will get this product terms. Next F2, 1, 2, 1, 2, 3, 4, 5. Group it. Okay. You will get this product terms. So here we have 3 product terms. Here we have 4 product terms. Next, the third K-map shows that F1, F2, F1. F1 into F1. F2 means here what is there? 1 is there, no? 1. In both the functions 1 is there, write it. In both the functions 3 is there, no? Write it. In both the functions 4 is there, no? Write it. And then group it. Is it clear to you? Yes? So here whichever terms are there commonly, write those. 2 is there, 3 is there, 4 is there. Okay? So group it and then write the prime implicants. So next we have here common terms yz, which is common here. 1 and 3 was common. Group it, we get the x bar z product here. Plus what we have here? Here we have 1, 1, 1. We group it and we get this. First we had this. Next we wrote here. Okay. 2. Then we group this. We get x bar y for this. Next we have here like this also we can take for F1. Okay, F1 can be written like this, no, minimal sum. So 0, 1, 3, 4, minimal sum of F1. Next for F2, F2 minimal sum 1, 2, 3, we get this, isn't it? Yes. So this is F1 minimal sum. So this is F1 minimal sum. This is F2 minimal sum. So here what we get the product term here? Concentrate on these two K maps, students. So here what we get? Tell me, one of you unmute and talk to me. What we get here for this? It is Y bar Z bar, isn't it? Next, here we get X bar Z. Same thing we have written here. Next, minimal sum, what we get here? This one, X Y bar. X Y bar here for this. Next, for this, what we get? X bar Z. We have written here. Next, for this, what we get? X bar Y. We have written here. So first you write the K map and then try to do the minimal sum for that. Okay, try to write the minimal sum for F1 and F2. Now here the question was asked was you have to realize 3 cross 4 cross 2, isn't it? 3 is the number of input lines. This is X, Y, Z. Number of input lines. We get here X, X bar. We get here X, X bar. Here we get Y, Y bar. Next here we get Z, Z bar. So how many distinct product terms are there? I will write F1 product terms. I will write here. Okay. X bar Z and Y bar Z bar. F1 has two product terms. Next F2, what all product terms are there? X bar Y, X bar Z, X Y bar. So totally how many? F1 is having 2, F2 is having 3, but you can see here this one X bar Z, here also X bar Z, isn't it? So same common term is there. So totally we have 4 different product terms, isn't it? So we have X bar Z which is present in F1 also, F2 also. So we have put a cross mark here. Okay. Next, Y bar Z bar. It is present only in F1. So we have put a cross mark here. Next, here is X bar Y which is present only in F2. We have put a cross mark. Okay. Next we have X Y bar product term which is present in F2. So we have put a cross mark here, F2. Okay. So any doubts in this? So students, here given a problem F1, F2, you have to implement it using 3 cross 4 cross 2 means 3 is number of input, 4 product terms, 2 output lines. First you have to write this, you have to make the pairs in such a way that it should be a common here, common. You can see cell 1 and 3 is there here, here also cell 1 and 3 is there. So it will yield X bar Z. X bar Z pair is common in both F1 and F2. You have to make a pair in such a way that you get a distinct 4 product terms. Okay. So X bar Z. How do you get X bar Z? Here X bar Z. Here Y bar Z bar. Here Y bar Z bar. Here. Next here X bar Y. Here. Next here X Y bar. So in this way you will realize these 4 product terms. Whichever are there in F1, put a cross mark. Whichever are there in F2, put a cross mark. This will realize function F1 and F2. Okay. You make a pair in such a way that it is common in F1 and F2 functions. 1 and 3 is common here. 1 and 3 is also there here. Make a pair. which yields x bars, and so it will be present in both the function f1 f2. So you will get 4 distinct product terms. In this way you have to solve this PLA.